Hey, looking at the binomial theorem, which we talked about briefly in class, dealing with Pascal's triangle and, oh, what was that? And other such stuff. Um, but the binomial theorem, what we are going to use it for is a method of expanding binomials, such as x plus 7 to the 12th. If you wanted to expand all of that, you could write it out 12 times and then do a buttload of foiling type stuff, but it's a lot easier to use your binomial theorem. And part of the binomial theorem is combinations, something we're going to use in our next chapter, which is statistics, but it's also used in the binomial theorem. And a combination, you may have seen these before in Algebra 2, you should have. It's n choose r. It can also be written as this little parentheses fraction looking thing without the fraction bar, but that can be read as n choose r, n taken r at a time, something like that. And this is how you would compute n choose r. It's n factorial over n minus r factorial times r factorial. And the way we would do that, and by the way, that is n factorial. That's not n with enthusiasm. That's not n, hey! No, it's just n factorial. And the way you do this, n choose r, it starts with n factorial. So 5 choose 2 would be 5 factorial over n minus r. So in this case, that'd be 5 minus 2 factorial times r factorial, which in this case is 2 factorial. Then we would clean that up. 5 factorial over 5 minus 2 is 3 factorial and 2 factorial. And in case you've forgotten what factorial means, you should have seen this before, but 5 factorial is 5 times 4 times 3 times 2 times 1 over 3 factorial is 3 times 2 times 1, and 2 factorial would be 2 times 1. It's the product of every whole number leading up to whatever the number is. And then we would need to clean this up. Now, there is a little trick that you can do in simplifying this. Rather than do 5 times 4 times 3 times 2 times 1 and clean up the numerator, this is all multiplication, so we get to simplify a little bit. For example, I can cancel my 3s. I have 3, you can cancel 3. This 2 can cancel that 2. The 1s are insignificant. I guess we could cancel the 1s. And then I could also say 2, have a 2, a 5, 4, and a 2. I could say 2 goes into 4 twice. And if you look at everything that's left, we have 5 times 2 over 1. And that's not too hard. 5 times 2 is 10 over 1, or 10. So 5 choose 2 is just 10. 8 choose 6 would set up the same way. 8 factorial over 8 minus 6 factorial times 6 factorial, and we would clean that up. So 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 over 8 minus 6 is 2 factorial, right? So this right here is 2 factorial, so that would be 2 times 1. And then 6 factorial is going to be 6 times 5 times 4 times 3 times 2 times 1. And then we start canceling. All of these are going to cancel all of those. 6 factorials will cancel. 2 goes into 8 4 times. And I'm left with 4 times 7. That's supposed to be an 8. 4 times 7 is 28 over 1. And you get 28. Now, I've shown you that, but I'm actually going to be okay if you do this in the calculator. Just the math teacher in me, the Math League of America in me, made me want to show you how to do this by hand. But there is actually a combination feature in your calculator. So let me show you how to do combinations in your calculator. Here's my screen for a TI-89. Let me turn that on. See, I don't need the y equals screen. So let me go back to my home screen. And the way that you do combinations in a TI-89 is you hit the catalog button, which the catalog button is right there. So I'm going to hit the catalog button. And when I hit the catalog button, every single command in the calculator shows up. And this is n choose r. So we're going to look for NCR. So let's see, I hit the N button, and there it is. It's the very first one. And at the bottom, it simply tells you expression 1, comma, expression 2. That means when I choose NCR, that last problem was, what was it? it was 8 choose 6. So if I wanted to do 8 choose 6, I'll simply hit 8 comma 6. So NCR 8 comma 6, and you get an answer of 28. So that's how you can do this on the TI-89. If you have a TI-84, it is a little bit different. So let's look at a TI-84. Rather than hitting the on button, let's get out of there. Second quit. There we go. There is a math button, and the math button is right here under alpha. So I'll hit the math button, and when I hit the math button, it opens up this menu, and at the very top on the far right is PRB. That stands for probability, and this is where all of your probability and statistics commands are. And we want to do NCR. Now NCR is the third option. On the 84, it works a little bit differently. You actually don't choose the NCR first. What we're going to do, if we're going to do 8 choose 6, you actually hit 8 first. Then you go back and you will find the NCR command. So I'll go over PRB, hit math, go to probability, choose NCR. And it's 8 choose 6 this way. So you do 8 NCR 6, hit enter, and you get 28. So those are the two ways that you can do combinations on a calculator. Get that out of the way. And let me write that in here in notes for you. And there you go. So that's how it looks when you punch it in on the 89 or on the 83/84. And how we're going to use the combinations is it's actually used to get the coefficients of your expansion. This is a generic mathy definition with a plus b to some n exponent, where the top number is always n, the bottom number starts at 0 and counts up through n. This is very confusing for people, so rather than do one with this vague n, I'm going to do an example with real numbers. And we did talk about already in class that the variables a plus b, it starts off with a to the 7th and then b to the 0. And then plus something times, and then my a's go down by 1 and my b's go up by 1. So b to the 1st plus something times, a goes down by 1, b goes up by 1. And then we'll finish that up. There you go. So we start with a to the 7th, b to the 0, then the a's go down and the b's go up until you finish with a to the 0, b to the 7th. And that's what I was trying to show you up here, a to the n, b 0, finishing a to the 0, b n. Then the coefficients, the numbers that go in front, are combinations. And in all of these combinations, let me go ahead and set up all these parentheses and then I'll fill them in. There we go. So in all these combinations, the top number is always the same as the exponent. So it's going to be 7 choose something all the way across. 7 choose something all the way across. And then you start at 0 and you count up. 1, 7 choose 2, 7 choose 3, 7 choose 4, 7 choose 5, 7 choose 6, 7 choose 7. And then a few patterns. The bottom number is starting at 0 and it counts up to the ending number. Something else, the bottom number is always the same as this number. So the bottom number is always the same as the exponent on the second term. Another pattern you may have noticed is the two exponents, like right here you have 2 and 5. They always add to your original exponent. So I started with something to the 7th, so all of my a plus b, my a and b exponents should add up to 7. And then the last thing is that this number on the bottom right here, this number, which is the same as b to the 4th, that number, that is always 1 less than the term number. And those are some patterns that you need to remember. And you'll see why in a little bit when we do real examples. So that number is always 1 less than the term number. And what I mean by that is, like this is my first term, and the number on bottom was 0. That's 1 less than the term number. This is my third term, and my number on bottom is 2. It's 1 less than the term number. 1, 2, 3, 4, 5, 6. This is my sixth term, and the number on bottom is 5. So that's what I mean by 1 less than the term number. I guess I should put an R there. And we're going to use those patterns to expand some binomials. So let's do a few examples. Complete expand. I'm pretty sure that's supposed to be completely. Yeah, there we go, fixed it. So if I want you to completely expand something, I have x plus 3 to the 6th. In this case, it's like my a term is x and my b term is 3. And when I expand this, I know it's going to be something times, it starts off with x to the 6th and then 3 to the 0th power plus something times x to the 5th. My x's go down by 1, and then my second term will go up by 1. So then 3 to the 1st power. And then I'm going to pause this and continue writing all of the rest of them. There we go. So they're all the exponent parts. My x's go down by 1. They start at 6 and go down. My 3 start at 0, and then we count up. And then the numbers in front are those combinations. They'll all be 6 because my original exponent is 6. Choose, and I start at 0. My next one is 6. Choose 1. My next one is 6. Choose 2. 6. Choose 3, and so on and so forth. There we go. And then the very last thing I'm going to want you to do is to actually compute these coefficients in the front. 6 choose 0, 6 choose 1. We need to compute those, but like I said, I'm okay if you want to do those in the calculator. So we will simply, whoops, that's not what I wanted to do. We will simply do all of those in the calculator, and we will end up with 6 choose 0, which is 1, times x to the 6, 3 to the 0, plus 6 choose 1, which is 6, x to the 5th, times 3 to the 1st, plus, see, I'll underline my terms. 6 choose 2 is going to be 15, x to the 4th, 3 squared, plus, and we'll continue computing each one of these, 6 choose 0, 1, 2, 3, so on and so forth until we finish. So I'm going to pause it while I do those. There we go. So we compute each one of those, and this is what you end up with for your final term answer. And this is where I may be different than some other teachers. If you are completely expanding something, meaning I want you to write every single term, I'm okay if you don't simplify these. And what I mean by that is, like, I could, just for example, if I pulled out this term right here, 15 times x to the 4th times 3 squared, I could write that as 15 times x to the 4th. 3 squared ends up being 9, and 15 times 9 is 135. So that term individually cleans up to 135 x to the 4th. But if I'm wanting you to write the entire expansion, I'm okay if you stop with my terms, with the terms being unsimplified. Now, if I ask you only for, say, the 5th term, or say on this one, if I only wanted you to give me the 3rd term, then if I only want one term, it's not too much to ask you to clean up just that one term. But if I want the entire expansion, then I'm okay if you leave them unsimplified. So let's do another expansion. Completely expand x minus 3y to the 4th. And this one you have to be careful because my second term, it's x, but then it's minus 3y. You need to include that negative as part of the second term. So b is actually going to be negative 3y. My first term, a, is just x. So when I'm expanding this, it's going to equal something times my first term, which is x to the 4th power, and then my second term is negative 3y to the 0 power. And you have to group that negative 3y with each one of those terms. Then the next one is going to be x to the 3rd power and negative 3y to the 1st power, plus something x to the 2nd power, negative 3y to the 2nd power. My x's are going down by 1. My second term is going up by 1 each time. All right, so there are my exponents taken care of. Now we need to find the coefficients, and my coefficients are going to be all 4 choose something. And remember, you start at 0 and you count your way up. So 4 choose 0, 4 choose 1, 4 choose 2, 4 choose 3, and 4 choose 4. And then we will punch those in the calculator, which will end up giving you 4 choose 0 is 1 times x to the 4th times negative 3y to the 0, which negative 3y to the 0 is 1. You may not want to write that term, and I'm okay with that. 4 choose 1 is 4, x cubed, negative 3y to the 1st, plus the next one is going to be 6 x squared, negative 3y squared, and we will continue computing each of those combinations all the way across. And there we are, and we're done. We can stop right there. If I want you to do the full expansion, I'm okay if you leave the terms unsimplified. You can stop right here. Also, don't forget there is that other little trick, well, that other trick I showed you where you start off with a coefficient of 1, and to get the next coefficient, you do the exponent on x. So 4 times 1 is 4, and you divide by the term number. That's the first term. So 4 times 1 is 4, divided by 1 gives you another 4, which is that term. Then I could do 3 times 4 is 12, and this is my second term. So if I do 12 divided by 2, you get 6, which ended up being that term. So you could use that technique also. You don't have to. To me, that technique's a little bit quicker if you're doing a full expansion. The binomial theorem, or the combinations, work better for a problem like what we're about to do. And that's problems like this where I only want you to find the fifth term. I'm not asking you to do a full expansion. I only want the fifth term. And this is where those patterns, let me go back to this page. This is where these patterns that I was showing you come into play, where the exponents here always add up to your original exponent. The bottom number in the combination is always the same as the exponent on the second term, which is 1 less than the term number. Those are the things you're going to need to know to be able to do these types of problems where I want you to find a specific term. I know the fifth term is going to be something, choose something. I know my terms are a and negative 3, so it's going to be a to some exponent and negative 3 to some exponent. And what I need to figure out is what is the exponent on a, what is the exponent on negative 3. I know the combination starts with 12, choose something, because the exponent here is always the same as the top number in the combination. And I want the fifth term. Now, I told you that the number on the bottom of the combination and the exponent on the second term is always the same. And I also said that that number is 1 less than your original, than the term number. So if I want the fifth term, 5 minus 1 is 4. So since I want the fifth term, you subtract 1, and you know that that bottom number is going to be 4. So it's going to be 12, choose 4. And the number on bottom is also the same as the exponent on 3. And then I remembered that these two exponents on the a and the negative 3 have to add up to your original exponent. So this one has to be a to the 8th because these two need to add up to the 12th. And then once I get my general structure, then I'll go to my calculator and I'll compute 12 choose 4. And 12 choose 4 is 495. A to the 8th won't clean up. Now I'm asking you for a specific term number, so if I want a specific term number, then I want you to actually compute negative 3 to the 4th, and negative 3 to the 4th is 81, and then we will multiply 495 times 81, and you'll get an answer of 40,095. So my final answer is going to be 40,095, 40,095, a to the 8th, and that is going to be the fifth term. If I were to expand this all the way out, my fifth term would end up being 40,095. Let's see, how many more did I have? 1, 2, no, just one more. Interesting, I thought I had another one. All right, so I want the seventh term of this one. We're going to use the same trick. I know it's going to be some combination times 2x squared to some exponent, 2x squared to some exponent, times 3y, because that's my second term, it's a positive 3y, to some exponent. I know the exponent on my 3y term is going to be the same as the bottom number in my combination, and I know the top number of the combination is always the same as the original exponent. Let's see if it's the seventh term. 7 minus 1 is equal to 6, so that means it's going to be 10 choose 6 and 3y to the 6. And then I know that these two numbers have to add up to 10. And last I checked, 6 plus 4 is equal to 10. So there is your structure to find the seventh term, and then the calculator is going to do the rest for us. All right, 10 choose 6 is 210. So it's going to be 210. Then we have to do 2x squared all to the fourth, which means we need to do 2 to the fourth. 2 to the fourth is 16. X squared to the fourth, you multiply the exponents, you get x to the eighth. And then 3 to the sixth, is it 729? 3 to the sixth is 729. So 3 to the sixth is 729 times y to the sixth. And then we will multiply all that together. 210 times 16 times 729. And you very often get pretty massive numbers when you do this one. This one is 2,449,440. And then I have x to the 8th, y to the 6th, and there is your 7th term. And 20 and a half minutes. That's exciting. All right, there we go.